Hello, everybody. I'm Andrei, and I work for JetBrains as a Senior Vice President of Investments, Research, and Education. Welcome to Regionals. Great things happen when great minds come together. JetBrains wants to seek out great minds all across the globe, support their initiatives, and work together to create great things that will make the world a better place. That's why JetBrains is proud to be a Global Tools sponsor of the ICPC. There are already many great minds working at JetBrains, and together we have created some amazing things, like the Kotlin programming language, for example. It keeps on growing and growing in popularity. In 2017, Google began officially supporting Kotlin as a language for writing Android applications. We have also created professional development tools like Cline for C++ programmers, IntelliJ IDEA for Java, PyCharm for Python, and also educational tools that help people learn and teach programming. The regionals are the biggest contest in the ICPC calendar. Thousands of talented people all over the world team up to solve complex real world challenges. These contests are the proving ground for future champions. But even if you don't make it through to the finals, the experience of competing in the regionals and the new friends you'll make along the way are priceless. Enjoy the ride. Best of luck to everyone.
And now the next problem is cubical romance. We actually expected more accepted solutions for this one. And interestingly, even though there is only one solution, the team that solved it was not in like the top, even I think even in the first page. So yeah, I think it was something that was missed by the top teams. Its author is Kevin, and it will be explained by him.
All right, thank you. So in this problem, you're given a bunch of numbers and you want to find a permutation of the numbers that is cubic. That is, there's a cubic polynomial that generates the numbers. So one common or one well-known thing about cubic polynomials or sequences of numbers generated by polynomials is that usually a few consecutive numbers are enough to generate the whole sequence. For example, if you have a quadratic sequence, you only need three consecutive numbers to generate all the numbers, the infinite sequence to the left and right. So in our case, we want a cubic polynomial, so we only need four consecutive numbers. So if we can find four consecutive numbers, we can generate the whole array using, for example, the recurrence above. That recurrence can be uh, computed for any degree. That basically just involves binomial coefficients. So the first step to solve this problem is actually to try something simpler. Instead of trying cubics, try quadratics first. So this is a bit easier. We only want three consecutive numbers. And we also know that degree 2 polynomials only look like one of these things, either a parabola opening up or a parabola opening down or a line. Okay, and we can see that the hardest part is probably discovering or solving the parabola case. So, okay, so that's the classification. Next slide, please. All right, so we know the three cases: parabolas opening up, down, or just a line. Okay, so how do we find three consecutive numbers? One conspicuous point in a parabola is its vertex, because that contains the smallest numbers. So that suggests to us to look at the smallest numbers, because those numbers will probably be consecutive. And indeed, that's the case for a polynomial of degree 2. For example, if your range contains the vertex, then the three smallest numbers will probably be near that vertex. So using those three smallest numbers, you can actually generate the whole array now. Of course, you don't know the order yet, but since there are only 6 possible orders, you can just try them all. So similarly, for the other cases, you can do something similar. Okay, so we move on to cubics. Cubics are a bit more complicated because they the shapes are far more varied than just a parabola. Even a degree 3 polynomial has multiple possible shapes. For example, it can have two humps, or I mean the a local maximum and a local minimum, or it can have no humps. And that makes things a bit more complicated. Our previous solution of finding the smallest numbers may not work anymore because of these weird shapes. It's not quite as regular anymore as parabolas. All right, next slide, please. So the insight here is actually it's not that bad, really. Even though the smallest numbers are not anymore collecting in a single place, it can still only collect in two different places, namely one of the ends and one of the humps, and nowhere else. Therefore, next slide, please. We know how to find four consecutive numbers because 4 out of the 7 smallest numbers must be on the same place where they collect. Therefore, take the 7 smallest numbers and 4 of them will be consecutive. And then for every choice of 4 numbers, just try all permutations as the order. You can cut the number of permutations in half because reversing the array is equivalent. So actually, that's the solution. There are only around 420 candidates to try. And for each candidate, you can check if it works in linear time by using something like a map or something. All right, next slide, please. So I said the constant is around 420, but in practice, that constant is actually much smaller because you can stop the check if you immediately know that it fails. And with great likelihood, most choices for the 4 numbers will actually fail because cubics are not that flexible. So I think that's to be expected. Anyway, there's a way to trigger the worst case on some solutions, which is, for example, this case where they're all ones except for a single element. So a naive solution will try all possible collections of 4 numbers out of the 7 smallest numbers, and they will all almost generate the whole array except for one, which will fail. Therefore, it will generate the worst case of 420. So this one is easily fixed though. Just try distinct elements, or I mean distinct collections of 4 numbers. Don't repeat what you've already done. All right.